What if a doctor could look at a brain scan and not just see an image, but instantly and perfectly understand it? Well, today, we're actually going to build that doctor. It's an AI, and it's designed to do just one thing: analyze a complex MRI and tell us, with incredible accuracy, if there's a tumor and exactly what kind it is. So let's dive in and see how it works.
Okay, so take a look at this scan. To you and me, it's a bunch of grays and whites, right? To a trained radiologist, it's telling a story. But to a machine, it's just a sea of pixels. So the real challenge here is teaching an AI to see the subtle patterns that a human expert spends years learning to recognize. How does it possibly learn to tell the difference between a healthy brain and 3 different kinds of tumors? That's the puzzle we're going to solve.
All right, so first up, the MRI challenge. Before we can get our AI to learn anything, we've got to clearly define its job. What exactly is the problem we're asking it to solve, and what kind of data is it going to use to learn?
So the goal itself sounds pretty simple, but the stakes are, incredibly high. We're going to feed the AI a brain MRI. It'll process the image, and then it has to make one single crucial decision. Which of 4 categories does this scan belong to? It's a classic, but absolutely critical classification task.
And here they are, the 4 possible answers. So you see, it's not just a simple yes or no on whether there's a tumor. The AI has to learn the subtle differences between 3 specific tumor types: glioma, meningioma, and pituitary. Or, of course, correctly identify a scan as having no tumor at all. Each one of these means something completely different for a patient, so getting it right is everything.
Okay, and this is super important. To make sure our AI is actually learning and not just, memorizing the answers for the test, we split up our data. Think of it like this. It gets to study the giant pile of images on the left, but its final exam is a pop quiz with images on the right that it has never, ever seen before. This is absolutely crucial. It forces the AI to generalize what it's learned, not just memorize pictures.
Okay, so we've got the problem. Now let's talk about the solution. This is the anatomy of our AI doctor. And just to be clear, we're not just grabbing some generic model off the shelf. Nope, we're building a specialist, a custom hybrid AI that combines a few really powerful ideas into one.
Yeah, this really is the secret sauce. Think of it like a master chef creating a new dish. Instead of using just one ingredient, our model is a hybrid. It's carefully blending different, powerful AI abilities to create something new that's perfectly suited for this very specific medical task.
So, ingredient number 1 is something called channel attention. Imagine the AI is looking at an image, and it's getting all this data, right? It's like listening to a huge orchestra. A lot of it is just background noise. Well, this component, it's like a sound engineer. It listens to everything and figures out which instruments, which feature channels, are the ones basically screaming, "Hey, tumor over here!" And it cranks their volume way up while turning all the other noise down.
Okay, next up, spatial attention. So if that first part figured out what to listen for, this next part figures out where in the image that important stuff is happening. It's like giving the AI a magnifying glass and a highlighter. It helps it zero in on the exact spots, the exact pixels in the scan that really matter for making a diagnosis.
And the final, crucial piece of this puzzle is the transformer head. This is the part that allows the AI to step back and see the big picture. It's not just looking at tiny little patches of pixels in isolation, no. It's understanding how different parts of the brain scan relate to each other, even if they're far apart. This gives the model that all-important context, just like a human doctor would.
So let's put it all together. We start with a really solid foundation, a vision model called ResNet-18. Then we bolt on our specialists: channel attention to focus on what's important, spatial attention to focus on where it is, and a transformer to see the whole picture. And boom, together they become our AI doctor.
All right, on to part 3, training the digital brain. So, we've designed our AI, but right now, it's just a blueprint. It's an empty shell. It doesn't know a thing. So it's time to send it to AI medical school. This is the training phase, where it's going to learn from thousands and thousands of examples.
But yeah, that kind of begs the question, right? How does an AI actually learn from just looking at pictures? It's not some kind of magic. It's really a very methodical process of trial and error, repeated over and over and over again.
Okay, here's how it works. The AI gets shown an image that's already labeled. Let's say it's a glioma tumor. It takes a guess, and at first that guess is totally random and almost certainly wrong. Then it gets corrected. It's told the right answer, and it makes a tiny little adjustment to its internal wiring to try and be a little bit better next time. Now imagine doing that thousands of times, over and over, for 50 full cycles. We call those epics. It's like 50 semesters of intense study.
And you can actually see that learning process happening right here on this chart. It's pretty cool. On the left, you've got loss, which is just a fancy word for its error rate. See that blue line? It's just plummeting down towards 0. And at the exact same time, look over on the right at accuracy. That green line is just climbing and climbing, getting incredibly close to perfect. This is the proof, right here, that our AI is actually getting smarter.
So after 50 intense epochs, medical school is officially over. It's graduation day. But first, the final exam. We're going to test our AI on that set of images it's never laid eyes on before. So the big question is, did all that training actually pay off?
And the answer? Oh yeah, it paid off. The final accuracy on brand new, completely unseen data, an incredible 98.78%. I mean, think about that. In a field where even human experts can sometimes disagree, that is a phenomenal score. It tells us the model didn't just memorize, it truly learned.
So 98.78% is a great headline, but this chart, called the confusion matrix, tells the whole story. Just look at that strong diagonal line. That means it correctly identified 271 meningiomas as meningiomas, 251 gliomas as gliomas, and so on. All those other little numbers off the diagonal, those are the mistakes. And as you can see, they are few and far between.
And if we zoom in even more, this scorecard breaks it down by tumor type. The two big numbers to look at here are precision, which basically asks, when it says something is a tumor, how often is it right? And recall, which asks, of all the tumors that were actually there, how many did it successfully find? And look at those scores, especially for pituitary tumors, over 99%. It's not just good on average, it's rock solid for each specific case.
And this last chart, it's basically a graph of the model's confidence. Now, you don't need to be a data scientist to get this. All you need to know is that a perfect model would have lines that shoot straight up the left side and then zip across the top. And as you can see, our lines are hugging that top left corner pretty darn tight. That's the sign of a really, really confident and reliable model.
Okay, so the results are, well, they're phenomenal. But here's the thing. In medicine, amazing results aren't quite enough. We need to be able to trust the process. We need to peek inside the AI's mind and actually understand why it's making the decisions it's making.
Yeah, this gets at the classic black box problem you always hear about with AI. The model spits out a correct answer, but it can't tell you how it got there. And in a field like medicine, where lives are on the line, that's just not going to fly. We can't trust it if we don't understand it. But thankfully, we've got a way to crack that box wide open. The tool is called Grad-CAM. And I want you to think of it like this. It lets us ask the AI, okay, you made a decision. Now show me your work. Show me the evidence. And in response, the AI creates this heat map and overlays it right on top of the original MRI. The bright red hotspots, those are the exact pixels the AI was looking at when it made its diagnosis. Suddenly, it's not a black box anymore. It's an open book.
And, you know, that really brings us to the heart of it all. We've built an AI that can not only diagnose with astounding accuracy, but it can turn around and show a human doctor, visually, why it thinks what it thinks. See, this was never about replacing doctors. It's about building them the most powerful, most trustworthy co-pilot imaginable. So the real question to leave you with isn't just about what this AI can do today, but what new frontiers in medicine are now possible because it exists.